All right, so let's look at the questions from the checkpoint for Module 9. So first of all, if a function's first derivative is negative at a certain point, what does that tell you? So first derivative of a function tells you about a function and its rate of change, so whether it's increasing or decreasing. So one thing I'll point out is that the concavity can only be determined by the second derivative, so I'm going to rule those out. If your first derivative is negative, let's look at these, the minimum and maximum. You can only have, so if you have a relative minimum or maximum, that's where the first derivative is 0. You might have absolute min or max at a point where the derivative is negative, but we can't say that. The function is increasing. That is not the truth, because if a function is increasing, that means its derivative is positive. If a function is negative, the only one that makes sense is functions decreasing. All right, next. AB is a local minimum. What is true about f prime of A? For the same reason as I kind of mentioned, if we have a local minimum, your derivative cannot be negative because that means a decrease. If your function has a local minimum, it's not decreasing at that point. It's also not increasing. If you have a local minimum, that only happens in one of two cases: is if the derivative is 0, if you have a critical point, or if the derivative doesn't exist. So this is our only possibility here. Question 3, f is a polynomial function. So why does it tell us a polynomial function? If it's a polynomial function, that tells you that your function is twice differentiable. It's infinitely differentiable, so it's twice differentiable. So we are told as a hint to try to graph this thing, so let's do it. Try graphing the first derivative using the points in the table. Okay, so let's graph f prime of x. So -2, 3. Let me encroach on the choices here, that's fine. So -2, 3, 0, 1, 3, 4. 5, 7. Okay, getting out of scale a little bit. We'll be all right. And 6, 5. Okay, so it's a polynomial function, so I know that I can connect these with a differentiable curve. Okay. All right. What does this mean? F has at least 2 relative extrema. Why would F have relative extrema? So for F to have a relative extremum, then my derivative would have to go from negative to positive or positive to negative. This is only positive. So I got to throw that one out. F is increasing. Don't know if I can say that, because I'm only given 5 data points here. For F to be increased, and that means that F prime would have to be positive everywhere. It's clearly positive at the 5 points I know about, but I don't know, maybe I'm going to write down something that's not, this might not be true, but it's not impossible. Maybe F prime of -1 is equal to -2. That's possible. So because of that possibility, I'm really leaning on the word must here. So basically, I'm trying to rule some of these things out. And I should probably revisit the first one here. I said that f could not have two relative extrema. It might, but I also give a case where it doesn't. So the fact that I can give that case means that saying that it must be true is impossible. The graph of f is concave up. So remember, this is the graph of f prime. What does it mean for a graph to be concave, the graph of f to be concave up? That means that f double prime of x is positive. I think this one I can say is absolutely false, because if my graph of f was concave up, that means that f prime would be increasing everywhere, which I already know it can't be. So f prime increases from -2 to 0. So I can throw that one in. The graph of f has at least 2 points of inflection. So what is a point of inflection? The point of inflection happens where the concavity goes from negative to positive, or vice versa. On my graph, my first derivative goes from decreasing to increasing at about x equals 0. And it also goes from increasing to decreasing somewhere around x equals 5. So that one, and it says at least 2 points of inflection. I think this one has to be true. Well, let's go back again. F has no critical points. I don't think I can say it doesn't, because I said f prime of -1 equals -2. That might be true. What if I cross out -2 and write 0? Is that impossible? That's not impossible. So I think I can't say that f has no critical points. So I'm going to go with choice B being correct. Question 4, which of the following must be true? The graph of f changes concavity in the interval 0, 2. So it's concave up. So it goes from concave up, concave down. Sorry, concave up to f double prime of 1 is 0. So I'm going to circle that one. I think that one has to be true, but let's keep looking. F has a local max at x equals 1. That very well could be true, but I don't think, again, must. Actually, that might even be impossible, because the first derivative, I'm going to say that one, this one might not be true. So the second derivative, like this could be an inflection point, but an inflection point could look like this. There's no max or min right there. So we don't know anything about the first derivative, so we can't say that's true. F is increasing on the interval 0 to 2. So another thing there is equivalently f prime of x is positive. So we know our concavity goes from positive to inflection to negative, but that doesn't mean that the first derivative is ever positive. It could very well stay negative the entire time. F has a point of inflection x equals 1. Okay. At first glance, it seems like that has to be true, but what we don't know for sure is maybe we have a sign chart for the second derivative that looks like this. X equals 1, x equals 0, x equals 2. And this is f double prime of x. We know that we have a 0 here. We know we have a positive at 0 and a negative here. But I'm going to show you something that's not impossible. Maybe positive, 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 concave up, then concave up again, and then there's some other inflection point here. So something I've said in past videos is that when you have like an algebraic definition for a function and you find where that's equal to 0, you've also found that it's equal to 0 nowhere else. I don't know that this function, I know the second derivative of 4 points on this function. So I don't know that I have an inflection point at x equals 1, so I'm going to throw that one out. F is decreasing on the interval 0, 2. I think for the same exact reason that I threw out the third choice. So it's possible for this function to be decreasing everywhere in this interval. It's possible for the first derivative to be always positive or always negative. I can't say that either one of those is happening. Could be neither. I'm going to throw that one out. I think the only one I have to go with is f double prime has to change concavity somewhere in the interval 0, 2. I think it's very easy to imagine that it happens at x equals 1. But maybe it doesn't. But since it goes from positive to negative, it has to happen somewhere. All right, so question 5. We're given a first derivative. Okay, so we should use, this tells us to make a sign chart. And we're going to be asked about something about local extreme points. So where is this function? So one thing I think we should do first is this. Find where this function or where this derivative equals 0. So x minus 1 squared. Let's do this. I'm going to rewrite this. X times 1, x minus 1 times x minus 1 times x plus 4. That's equal to 0. So if I set these individual factors equal to 0, then what do I get? I get x equals 1, and then I get x equals 1 again, no new information, and x equals negative 4. So I have critical values at negative 4 and 1. And unlike the last question where we had the table, for this one, I can say, since I know how to categorize the derivative of this function everywhere. So now that I found the zeros, I can say with certainty that the derivative is equal to 0 nowhere else. So I have critical points at negative 4, positive 1, and absolutely nowhere else. But what's happening around those points? So if possible, I'd like to choose 0 as a test point. 0 is between negative 4 and 1. If I choose any value bigger than 1, I'll choose 2. And what's a good value to choose that's less than negative 4? How about negative 10? So what is f prime of negative 10? That's equal to negative 11 squared times negative 14. So this is going to come out to be a positive number times a negative number, so that's a negative number. How about f prime of 0? That's equal to negative 1 squared times 4. That'll be 4. So that's positive. But then what happens at 2? F prime of 2 is equal to 1 squared times 6. So that's 6, which is positive again. So what does that mean here? So now that we've done this, let's categorize the critical points. At x equals negative 4, we are decreasing, going horizontal, then increasing. That is a minimum. What is happening at x equals 1? We're increasing, coming to a horizontal, increasing again. That's not a minimum or a maximum. So because of this, I think I have one local minimum and no local maximum. Only correct choice is this one here. Moving on to question 7. Okay. So I'm given a function. I want to determine the location of all mins and maximums using the first derivative test. Okay. So that is the only test I'm allowed to use. So let's find the first derivative. How do I find the first derivative of natural log of x over x? I'm going to need the quotient rule. So what's the derivative of natural log of x? That's 1 over x multiplied by the denominator, so that's x, minus natural log of x times the derivative of x, which is 1, all over the denominator, which is x squared. So if I simplify a little bit, which I recommend, then what do I get here? I'm going to get 1 minus natural log of x over x squared. So where am I going to get critical points? One place, so basically I'm going to look for two things here. I want to look for where the derivative is equal to 0 and also where the derivative might not be defined. So where will this derivative equal 0? I'm going to multiply both sides of the equation by x squared, and then I get 1 minus natural log of x equals 0, or natural log of x equals 1, or x equals e. So that's one point. So I have one place where the derivative will equal 0. What about where places where the derivative will not be defined? So what would cause this thing not to be defined? So I have a derivative. What's the domain of this derivative? So I can't divide by 0. So I think that x being equal to 0 is something I can't do. But even more than that, also natural log is undefined at x equals 0, but it's also undefined for all negative numbers. So I think I can supersede x is not equal to 0 with x cannot be less than 0 or equal to 0, which is the same thing as saying that x has to be greater than 0. So my domain for the derivative is x greater than 0. So that actually helps me organize my sign chart a little bit. 0 is going to be the far left of my my sign chart here. So, which means the only critical point I have to worry about is e. So from 0 to e. So basically, what's my domain? My domain is x is greater than 0. The only critical point I found was e, which means I have to choose two test points. One between 0 and e, and one bigger than e. I'm going to choose 1 between 0 and e. And bigger than e, I'm going to choose 3. So at e, I know the first derivative, f prime, was equal to 0. What about at 1? So let's find that. F prime of 1 is equal to 1 minus natural log of 1 over 1 squared. That's equal to 1. So that's positive. What about f prime of 3? That's 1 minus natural log of 3 over 3 squared. Natural log of 3 is a number that's bigger than 1. So this is going to be a negative number. So what does this tell me? First of all, I think the sign chart can tell us something about relative extrema. So we have a function that increases, comes to a critical point, and then decreases. So because of that, I think I have a relative max at clearly x equals e. But if I need to find the y value that goes with that, I think we should. Actually, we're just looking at x value. So relative max at x equals e. Absolutely. About relative minimum, I can't have any relative min. So because I only have one critical point and I already found out that it was a relative max. So I've got the relative extrema all figured out. What about absolute? I think based on our graph here, We have a function that's everywhere increasing up to a point and then everywhere decreasing after that. That tells me that I can have, like, that our relative max is also an absolute max. What about absolute minimum? So my function is defined for every positive number. Which means the further I go right, the more this function is going to decrease. And because of that, I can have no absolute minimum. So I would encourage you to graph this function to, if you want to see a visual of it, but I believe we have to have a relative and absolute max wherever x equals e, but there are no relative or absolute minima. Actually, I don't know if I can say that. Let me think about this a little more. Yeah, I think that's true. Okay. Actually, I should probably show you a graph while I'm talking about it. So let's exit this for a bit. So it's natural log of x over x. Okay, so I suspect at this point where this maximum is, that's 2.718 as the approximate value of e. But if I zoom out, as I get closer and closer to the y-axis, I'm going to get smaller and smaller numbers. But what happens as I go further and further right? I believe I have a function that's going to decrease and decrease, not to negative infinity, but it's going to get closer and closer and closer to zero. But it's never going to reach zero, so that's why it has no absolute. Well, that's another way to say it has no minimum. It's going to keep approaching zero. The real reason it has no absolute minimum is that this behavior as I approach x equals zero. I'm just going to keep getting arbitrarily more negative numbers. So coming back to this question, or our last question here. So question 7. I have a function. I want to find the location of all mins and maxes using the second derivative test. So these are exponential functions. The domain of this function is going to be every value of x. So let's say this first. Basically, that we'll know that x can be any real number. So we want to use the second derivative test. So since we're being asked for that, we still need the first derivative to tell us where the critical points are. So f prime of x is equal to -6 e to the -2x plus 20 e to the -4x. Let's find the second derivative while we're at it. F double prime of x is equal to 12 e to the -2x minus 80 e to the -4x. So let's find the critical points here. So if I set this equal to 0, what can I do? I believe I can factor out any. Yeah, let's try factoring out a e to the -2x and see what happens. E to the -2x, I'll have -6 plus 20 e to the -2x. Is that correct? Yeah. So equals 0. So one thing we've said before is that if I set this exponential factor equals 0, that's never going to come with a solution. So what we really have is this 20 e to the negative 2x equals 6. So now let's solve for x. E to the negative 2x is equal to 6 over 20 or 3 over 10. And from there we get, if we take a natural log of both sides, we get negative 2x equals the natural log of 3 over 10. From there we divide by negative 2. So x is equal to negative 1/2 times the natural log of 3 over 10. So that is our only critical value. So we have a critical value. We're being told to use the second derivative test. I'm reading this over again. I don't know if we're meant to go after local min, or sorry, absolute mins and maxes, but let's go ahead and do both. So here's our critical point. Second derivative test will tell us what kind of critical point that is. So f double prime of, let's go ahead and approximate this, make it a little easier. So I'm getting an approximate value of this critical point as 0.602. So what is f double prime of 0.602? Is equal to 3.6 minus this doesn't look right. So 0.602 3.6 minus 7.2, so that comes out to be negative 3.6. It's less than 0. So what does that tell us? That tells us that we have a critical point where the second derivative is negative, which means we have to have a local max at x equals negative 1/2 natural log of 3 over 10. To find out about absolute mins and absolute maxes, let's go ahead and look at the graph. Because so it says all work must be provided when finding a derivative, but we can solve any equation using technology. So we have the derivatives we found by hand. I don't care. So 3 e to the negative 2x minus 5 e to the negative 4x All right, so here's the local max that we found. As far as local min, we have local, so we know we have no local min because we only have one critical point. But I think for the same reason before, we cannot have an absolute min because as we go left, this function just keeps decreasing. But also we have, it looks like our relative max is also our absolute max. So I think that's all for our checkpoint. Let me just make sure that was the last question. Yes, it was.